Good morning, everyone. The recording has started, and welcome to this webinar on estimation of shale gas and oil properties based on field data. It was actually one of the first papers I ever read in the oil and gas domain by Tao Yang and his colleagues from Equinor when he actually lived here in Houston, where I am right now. Obviously, I'm not Tao Yang. I'll introduce him in a second. But first, I'd like to cover some meeting logistics. We have over 300 registered participants, so everybody by default is, of course, muted, but that does not mean that you can't ask questions in the Q&A chat box, so you can do that down to the right. The presentation will be between, probably close to 45 minutes, 30 to 45 minutes, and then the rest will be Q&A. And just remind you again that this webinar is recorded. It's also facilitated by us here at Whitson, and we love this kind of stuff. We love PVT, we love equations, and we kind of exhibit that love through our software products, Whitson Plus and Whitson PVT. And if you're interested in learning more of that, you can go to our webpage and sign up for one of our trainings for the next year or any of the upcoming webinars. If you love in person, you can also come to WhitCon in the fall of 2025. That's here in Houston. The date for that is 2nd of October, and that's for everyone that loves PVT, bottom pressures, RTA, flow material balance, etc. And we're looking forward to seeing you there. The next slide is actually put together by our office manager. I hope a lot of this is right, but what is not mentioned here, I think, is that Tao actually worked at what is now Whitson before he joined Equinor, where he is a chief professional. Tao has expertise that spans 300 fields worldwide, and he's been, as we'll talk about here, he was also a distinguished lecturer with SBE, and with that, I got something in my throat. Sorry about that. Tao, if you can share the screen, then we get started.
Yes, I'll do it. Hey. So is everything okay?
Yes, perfect.
Okay, very good. Thank you very much, Matthias, for the introduction. Yes, I have a very strong connection with Whitson. I have to say I learned so much from Whitson that's really built the foundation for the future. That this is really something very, very important. And this is a SPE distinction lecture selected for 2017 and 2018. And it's sort of like several years ago. And when Matthias asked me to make the presentation, and I look at the slide, and I found that there's a lot of things already changed. And the good news is, this is just a starting of our journey. So after this study in the US, and I went back to Norway, and we continue a large scale machine learning study, not only shale, and we're really doing all the conventional reservoirs as well. So let's start, and I will go through the slides. Hopefully, I try to not use too much time, and we can leave some real time for the questions. So this is a really fun part, okay? As you can see from the screen that the Statoil, that's where when I was in the US, that's changed the name to Equinor, and the logo also changed, and but the work still stay. We sold the asset actually, and to Talisman, later to Repsol, and the technology is still used in the same field. Okay, let me. Okay, this is outline, and we'll have some quick introductions about the PVT for the conventional reservoirs. And then by that time, shale gas and oil was new, and there are some challenges, especially for people like most of people working on conventional reservoirs quite a long time. We need to learn what is special with the shale gas and oil. And actually, what we found out is that's quite interesting one. It's quite simple actually compared with the conventional reservoirs. And so we will really talk about the most important is the third bullet points, how to estimate the oil and gas properties. If you don't have the PVT data, you can still do it. Okay, we have some application examples, and I'll come back to a conclusion. So this is a very interesting figure that was made in 2014, and the yellow part is actually this is the starting of the revolution of the shale gas and oil. And it's when I was in US, I was 2012. We're just at this very steep increasing, okay? And this is the energy agency. They make an outlook about this shale gas and oil, which they predict it will reach the kind of a peak in 2020 and will start to decline. This number, can you see this number on the top? This is today. Instead of a plateau and decline, we're just continuous increasing all the way to 13 billion barrel of oil. And it's amazing about how the technology can change really the game. Okay, this is in old days when people are very familiar with the conventional reservoir, how you work on it. You do exploration, appraisal, and then you put the big money into the project. You start the development, and you have a big investment, and your capital return is very long, many years. You get the money back. Okay, and of course, in 2012, people start to understand in a shale is very different. So you have a concept, you try, if it's working, and you ramp up, and then you start to look for new. And this is a very different mindset, and it's working really well. To come back to the basic description of PVT, and this is like the PVT guru standing, and he actually made a PVT correlation in 1940s. He said, if you give me the surface of gas, surface oil, and the ratio between these two, the GOR, and then he can actually tell you what is black hole properties, like a BO, bubble point, all this stuff. And this is his work. And his name stay in the industry because his work is really outstanding, because we still use the standing correlations, okay, even after so many years. And but the modern approach, like Whitson business, is different. So people nowadays, the standard one for the conventional reservoir, you take samples, you make a laboratory measurement, or you make a downhole measurement, okay? When you have the data, and then you kind of use the equational state model to match everything and make predictions. So if we look at this is the Eagle 4, like in Texas, and this is a picture from, I think it's from BP and from 2012, and you have quite a nice separation of the dry gas, wet gas, light oil, all the way to the black oil. And it's across very big area in Texas. And for the shale, that you don't really take a in situ representative sample. It's very difficult. And some people try, and they take the whole core out, and they try to find something. And the PVT data also is not very money. And the geochemistry, we have to really give a big acknowledgement about how the geochemistry work. And because of the fluid, they're not really moving around. So this gives the geochemist a super opportunity. Their prediction on the shale in the big area is always right. So this really make a big contribution to the so-called shale gas oil revolution in the US. But come to the small area, especially for your well, then you have to be very careful. And not even only for one well, for the small region. For example, you draw a big line here. This line is really like continuous like this. They're not. So you have the fluctuations and the changes. And so you have specific area where you buy, you have to be very careful because you can't really trust the basic model. And basic model give you a very good big picture, but not to the well, not to the small acreage you buy. This is a reservoir engineer made a simulation work Of course, all the people focus on fracture length, matrix, permeability, how many fracture numbers, and all this related with the hydraulic fracturing. And he shows CRUMA, he shows actually PVT. It's rather important in this Typhoon chart. This ranking shows you, like, especially for the oil. If you have a dry gas, it's actually negative correlation. If you want to look for oil, the condensate, and this is a very, very important thing you need to know. As I mentioned, that the people want to take the in situ representative sample, and some people use a pressure core. They take the whole core out and wash out the hydrocarbon and combine with released gas. This is one approach, and it's a research type, I would say, and it's not really like a standard industry practice. And this one actually, Whitson are heavily involved into this one. So basically, you can use a model, use a historical data. You can actually back calculate what is actually the original fluid they are. And if you look at the research domain, and over 90% of the publication, they're talking about the nanopore size, what is the impact, how much they change the bubble point pressure, dew point pressure, and it's a good activity. And but come to the industry practicalities, that's still very difficult to apply. So this is the main question that we're going to address in this presentation. And when you have no PVD samples, no measurement, and only some field data, the field data I mentioned is like you have some GOR, you have some gas data, surface gas, okay? And can you use this kind of limited information to estimate what is the PVT of the reservoir fluid PVT? And so for the shale, they're drilling. After drilling, they will do the completion. They will frac it, and so they have no time to wait. So there is no time to wait for you to finish the measurement in the lab. So it's very important. You need to have some data, maybe not as accurate as in a PVD lab, but it's good enough for them to make a decision for the well. So when we have all these unknowns, so especially in 2012, that's 10 years ago. So what we do is we actually look at Eagle Ford very, very carefully. And we did a very thorough study. We actually, because the Eagle Ford, not all the shale reservoirs, they are undersaturated. And Eagle Ford is a very much undersaturated, which is positive if you look at the initial fluid samples. And we take the samples. We have I have a co-author for the paper. Jamie, he's the manager in Statoil by that time. He actually really support this. And we did the measurement for dry gas, gas condensate, volatile oil, black oil. We did all of this stuff. And then we look at all the early productions. And all the samples were taken from early productions and 50 wells. And it's easy to talk, but difficult to do because it actually took 2 years to have the result. So before I moved to the US to take on this job, and actually Remy, he already started to order all these samples and PVT measurement. So that's really good. He basically put all the report on my table and said, can you find something from all this measurement? So this is what we did. We did quite a thorough analysis for all the 50 wells. And this is the most fundamental one we usually do. And you want to look at the characterization factor, which will tell you how many fluid system in a reservoir. They're quite, they're not exactly the same, but if you look at the error, plus or minus is 1%. If you draw an average in the middle, it's plus minus 1%, which is like a measurement error. So basically, we just assume they have a same fluid in the entire Eagle Ford. Such a big area is actually only one fluid system. And we look at the GOR and the API, the correlation. And GOR is quite, especially for gas condensate, and they are not plus minus 10%. You don't see very like a on the same line. No, they spread around. And you see that the higher the GUR, the API start to increase, which means you have a lighter and lighter fluid. And then cross over this line, you actually see when you have this very dry gas, okay, you start to not dry gas. Dry gas, you don't have condensate. You have some condensate, okay, which is a wet gas, very high GUR. And you start to see actually API start to drop. I have an example I will show you at why this happened. And this really help us for the business decision. Okay, but put it very simple. And the higher GUR, you have a lighter fluid, except for the very high GUR region. And this one is in a standings textbook in the 70s, and basically tell you that if you have a black oil, which is GUR 1000, you start, and your saturation pressure increase with the GUR. But when you start to change to gas condensate, and they are not increasing anymore, they are actually decreasing. So you can see this very clear from this correlation. And make some even more impressive correlation is, and this one you don't see it always in a conventional reservoir. This is very specific for the shale. And you have the GUR increase, and you have almost a monotonic increase of your C1, which is actually very good news. Okay, that makes things simple. And very surprising if you look at the C7 plus, which is a heavier fluid, and you start to see that with the GUR increase, you have a really monotonic decrease of the condensate, the heavier part. Okay, and this one can, this is the 50 wells from the entire Eagle Ford shale, and it's you don't have any surprises here. Okay, so what we find out is not always for, you have to look at the geology, but for Eagle Ford, and it's only one actually system here, and so wide range, and they cover for all the different fluid, and if you know the GUR, basically you know everything. So if you have a GUR, you can actually predict the composition, C1, C2, C3, all the way to C7 plus. You know the API. So why is so simple things become? This is I learned from my colleague Angel, and he's working together with me, and he coached me on a lot of things on the geochemistry. And this one is a simple plot showing how difficult it is for conventional reservoirs. After the fluid filled into the reservoir, there are so many things that can happen, and so many movement can happen. It really make your reservoir complicated. This is for the conventional one. But for the shale, because they're so tight, without the fracking, they're not moving. Basically, the rock holds the fluid. They're still in the kitchen and haven't really leave their home. This makes things very different. If you look at the fluid gradient, you have a conventional reservoir on the top because of gravity segregation. You have a gas, and then you have an oil. And you might have a gradient here, but a very little gradient in a gas zone. And this is the top to the bottom. So the question is, how about for the shale? As we've seen from Eagle Ford, the big piece of shale there is actually the shallow part is actually the oil. And the most deep part is the dry gas. And it's because of the kind of the temperature. This is a very much like a thermal maturity driven process. The gravity segregation doesn't work here at all. You have a continuous change from oil to gas. Some shale reservoirs, they only have half, like Marcellus or some, they just from gas condensate to the volatile oil and they finish. They don't have anything like a black oil. And Eagle Ford is very special. It's such a good learning case. So this is I already talked quite a lot because this is an extremely low permeability limit fluid migration, and the thermal maturity, basically the temperature, is the main thing that to decide how the fluid composition change, and if you come to the theory that why this happened is actually because the chemical equilibration is a closed system, and this really makes this happen. And this is why, like Calsap, a Danish company, they start to make a model to actually predict the composition if you tell them the temperature. Okay, so very much this is the conclusion. We want to estimate the fluid properties, then we need to know the GUR. If we know the GUR, then we get everything. And the question is how to get a GUR. So they start to have some difference compared with my original slide. And in the original slide is the dark blue color. So before the production, and actually the only thing you have is the mud gas. During the drilling, you have the mud gas released. So this one you can use to get the GUR. And after production, and you have a lot of data. You have GUR data, you have API, you have surface gas. All of this single data can be used to get your GUR. Okay, and this is gel cutting, and this is something new. And that's the one I will volunteer to do this second distinction lecture next year. And they will send me the schedule next year in April, and I will know where I will go. And this one is quite popular because same as the mud gas, they're available always. If you look at how much gel cuttings we store in the warehouse, it's like an IKEA furniture shop. Many buckets. We have cuttings for all thousands of wells. We like for Equinor. Same for other companies. And if you can take the stones, the small piece back, and crash it and measure the GUR, and this is fantastic because a lot of people even don't know what's the reservoir segment, what is the fluid inside. Okay, this is something that the people really like, and this journal Petrophysics, and they actually put this nice picture on the front page. So I will not spend more time on this. I will focus on the original one. I will mention the new development. So this is something is really working well, and you don't need a machine learning, and you just draw a correlation. And if you know the wetness of the separated gas, you actually know the GUR. This is working so well. Like of course you have some uncertainties, but compare with what? Compare with we don't have anything. This is brilliant. But this is a flow chart. What we do. And this is the original. This is the correlation based, and basically we build a correlation just like all the figures I show you. Okay, you just put either the GUR or the API gravity or the surface gas composition, which is like a separate gas, and the mud gas, the gas released from the drilling mud, or cuttings, the new things, and you can use the correlation. Actually, you can derive the composition, the black hole properties, even the NGL, all the stuff. Okay, and I mentioned that when I came back from US to Norway, and because we start to work on conventional reservoir, which is a lot more complicated. You can't draw a straight line anymore. So that's why we start to use. We become the very early digital pioneers. We use machine learning to solve this. You have a big database. You use machine learning, you can actually do it from the left hand to the right hand. So this is the applications, and I will show you some 3 examples. And basically, you have a kind of a timeline here. This is the before you start to produce, and this is the after you do the production. Before you don't have a lot of things. Basically, you have a mud gas and the gel cuttings. These are the one you can use. And after production, there's a lot of things you can use. As I mentioned, you can use a different gas API and get to the all the properties you need. The first example is actually separated gas, and this one is used so much because the number of wells in Eagle Ford is so big, and the production engineer, they need to do their simulation, and they need to have a composition. They need to have something to do their all this production simulation. So it's very important. All this network modeling, they need to have a composition. So where to get this composition? Okay, the live oil, live gas. It's not the surface gas. So here, the surface gas is the input, and the output is a live fluid. This is the kind of the input. This is the separated gas. This is the example. You get all this very dry, very lean, heavy part, and then you have a lot of C1, right? And then you use a correlation. It's Excel, actually correlation, Excel based, very simple. And my colleague Yang used Rusmalan, and he's an expert in coding all these plugins in Excel. Very simple. He just build the data, use our database, build all the correlation, and we input this one. We can get the well stream composition, and we can actually estimate the PVT properties, saturation pressure, API, GOR, formation volume factor. And my colleague, Alexandra Seeley, in 2021, she actually improved this one. The reason we use machine learning is because it's not because they're fancy. It's actually because the conventional reservoir is more complicated. And if you use a machine learning model, you can handle more parameters instead of just drawing the correlation in Excel. Okay, this is the most actually the people talk about the value creation, and this is a part. This part is very, very important because the people before they complete the well, and the PVT actually will have a big impact. And usually we don't have the PVT information. We have only the geochemistry basin model. And as I mentioned, it's a good model and it's good for the area, but it's not good for your single well. And it's very important you verify. You use a data-driven approach, not just assume something. So mud gas really start to really make a difference. And we have an example. This is a pilot well we actually did in the Eagle 4. And the data, this is the CGR. This is this red line. This actually is what we have. And this is wetness. Basically, this is raw data. You have the raw data, and then you translate directly into CGR. And you look at the production geo CGR. It's quite close, actually. And this is the work in 2014. And this actually became a starting point. And we start to do a lot of more. And when we build the machine learning model into this, and we extend it to conventional reservoirs. And this approach, we gave a name. We call it real-time reservoir fluid identification. The main reason is to call it real-time is helping the well decisions. And this one goes to the front page of JPT. And also we quite honored to get this 2022 the Digital Solution Award from World Oil. This is the last example. It's about buying things. Before you buy something, you have to make a quite thorough evaluation. And when you buy the Shale, and you have to make sure. And Eagle 4, when Equinor we bought it, and we've been told it's quite rich, a lot of condensate. When we start production, quite a lot of area we bought, they produce nothing, only dry gas. So this is very important that the condensate yield, that's the most important. Of course, also depend on your shale. If it's a black hole, that doesn't mean it's a good thing. And you might not produce anything. So it's very important to have that in mind. We have a asset actually somewhere north of USA, and this is the target area. This is where we want to buy. And we have a neighbor field to produce actually oil. And the geochemical basin model, and they are not really conclusive because they are saying that in this basin you have both gas and oil. It's very difficult for our BD team to decide if this is a gas and oil. They assume this is oil, but when we do this work, we actually have some separate gas data. They don't have a lot of good PVT sample at all. And we look at the separated gas, and you look at the wetness, and you have a rather actually gas. This is a gas-prone kind of a prospect. So that's why we told our people, and this is not a good thing to buy because they want to buy liquid rich. And also we have a support from this stock tank oil analysis. And actually, if you look at the carbon number, and this is from 7 and all the way to C36. And for the GUR around 200,000, you don't have a kind of an exponential decline. You actually, because basically the liquid is too little, and you lose all this part, and you start to get this almost like a biodegraded fluid. And for the normal, they are not biodegraded. This is a normal oil, but you lose all this light part. And if you have a 20,000 GR, you actually have a nice exponential distribution. So this gave us explanation about this because they look at the API, it's low, but we're telling them you have such a high GUR fluid here. That's why you have a low API. So this is actually not contradicting. It's actually supporting each other. So later, like we have a lot of more tools now to do this kind of a job, because now we can use standard mud gas, because the separated gas is not available for all the wells. And the standard mud gas, you have it for all the wells. And my colleague, he published some paper regarding use the standard mud gas. You can do the prospect evaluation. That gave a quite good result. And in addition, that this is our partner in APT, which is Applied Petroleum Technology. It's a geochemistry company in Norway. They're operating also in the US. And Michael, he actually is in the US. Michael is the biggest geochemistry expert from ConocoPhillips before. Okay, and Michael also, they did the work on the geocutting. They actually, all of this new method really provides some opportunity that people don't have it, this kind of chance, people don't have it before. And if you mask all this different data, and it's pretty sure you can make a much better decision than people just use like a geochemistry basic model. I'm not talking about the model is not good. It's not good to very specific well or a small area. Hey, come to these limitations. And if you use the field data, mud gas, geocutting, all these new things I talked about today, they are not as good as the PVT samples, period. Very simple. Because if you have a PVT sample, you can make a very detailed compositional analysis, you can make a property analysis, you get everything you need within like very small uncertainties. But use this new method, you don't. But it's a trade-off. The new method offer you opportunity. You can get the fluid properties anywhere you drill. And versus how many PVT samples we have per well. Usually you have a 1 or 2 with a complete full PVT measurement. So this is quite a small number. If I give you a big number, like a picture in Norway, like Equinor, we drill 5,000, 6,000 wells over 50 years time. And how many full PVT analysis we did on PVT samples? It's only 2,000. It's very little. So in a way, you have accuracy and you have availability. So I think we try to use all the good things. You don't want to use the new method and predict some property and overwrite your good PVT measurement. But on the other hand, for the area, you have nothing. And all this new method will help you to make a data-driven decision than just assume something. Typically, like when we do reservoir simulation, we have so many compartments, you start to assign the fluid compartment. And basically somebody tell you they are similar and you just assign. And that's not a data-driven approach, okay? And also the geology. That's something, It's very important for our PVT as well. Eagle 4 looks so nice. That doesn't mean all the other shale plays, they will be as nice as the Eagle 4 I show you. They might have a different geology. You might have two different fluid systems. And the most important thing I want to mention is the last one. You can't use the plot, the figure, the correlation I show you on Eagle 4 and apply to Marcellus, for example. And my colleague Ibnu, he did a study on Marcellus. He actually find out the correlation between the wetness and the GOR. They're parallel. One line is Eagle 4, another line is Marcellus. So this is what I'm talking about play dependence. And when you derive a correlation, you need a certain number of data. And if you don't have enough data, it's difficult to drive a correlation. But anyway, so if you don't have it, you might borrow the trend and you do a shift. And this is the only advice I can provide. Okay, this is the conclusions. And for the shale, and low permeability is very bad for production, but it's actually really help to make the PVT predictions because they make the fluid system very simple. And the second point is all the new things we talk about today, they can use to estimate the gas and oil properties with reasonable accuracy. It's not the best one, but the availability is the most important. You get the data instead you don't have the data. Okay, this is I think this is the last page, and this is what I put for this SPE distinguished lecture. It's very important that this is the teamwork, because I mentioned a lot of people, and there's a lot of people I didn't mention the name, and they provide a lot of help. And if you look at the last one, that's Whitson. And so it's really appreciated. And Curtis gave me a lot of support on this. And when I talk about this at the beginning, very few people actually believe me. And Curtis was one of the first to actually give us strong support. Okay, I will stop here, and I hope we'll have some questions.
Perfect, Tao. The first question is, can we have a PDF presentation?
Sorry?
The first question is, can you share the presentation?
Yes, we do.
Yeah. So we'll make sure that Tao sends it to us, and we'll distribute it after the fact. There's a lot of questions about, like, you kind of related to, you mentioned the GOR, and I think people were a little bit confused. Is this a producing GOR? Is it the in situ GOR? How do you think about that GOR in general? It's a lot of questions related to that.
So that's a very good question, and basically this is the expert's question. And when you come to the geoscience part, and they don't ask this kind of question. And when you make a correlation, you have to make sure that they are from the same base. For example, and we use single flash GOR for our machine learning. The reason is, it's not we believe a single flash GOR is the best GOR to use. It's because they are available for almost all the samples we have. And of course, you can always correct it afterwards. You correct from the single flash to more accurate, multi-stage GOR. So this is my answer. So this is come to the very similar as a question about accuracy. And when we talk about the error is like 30% plus minus, and people think that you're crazy. And if the data is plus minus 30%, is that any use? It's actually a lot of use. If you ask the people, the petrophysics, the geologists, the drillers, they appreciate very much if you give them a plus minus 30%, then don't give them anything. I hope this answers the question.
Yeah. I think kind of where the question comes from is probably that a lot of these tight unconventional basins, especially like Montney, Anadarko Basin, parts of the Delaware Basin as well, like the initial reservoir pressure is kind of at or even below the saturation pressure, or at least the saturation pressure you would measure in the laboratory. So how would you kind of deal with that or think about that in general?
I think the Marcellus have a similar situation. They're rather close to the reservoir pressure, close to the saturation pressure. And this is a rather difficult question to answer, actually. And so what we use almost the same approach. For example, we use the same approach from Eagle 4 to Marcellus and to predict the production, GOR, whatever. And we don't experience like a big drawback. And but if you challenge us about, you have a reservoir pressure actually lower than. So what happened in the shale reservoir? You have a gas and oil holding in the same pore space, and so what is the property there? So it's a difficult question, very difficult to answer. And so the thing is really come to, if you have a two-phase, and really come to which one flow and which one I stay, and the ratios, and that's very difficult to answer that. And I think we live in a kind of a world with a lot of uncertainties, and we try to catch the big picture. And like I said, that we use the same approach, and in Eagle 4, and quite many wells, including the gas and oil, and we didn't experience big problems like for us to do that. And so this is what I want to say. And we're all engineers, right? You need to do the work and try and error and learn. And if things actually, what I said, that doesn't work for your field, and then you need to really go back and find out better solutions and talk about here, right?
Yeah, no, for sure. And I guess kind of still on the GOR topic, you
Yes.
had GOR versus kind of like you kind of showed the correlation there. Is that kind of like a single stage GOR, like a zero flash GOR that you're plotting on the one axis there, or is it like a multi-stage one? Can you just
They
elaborate?
are single flash GOR.
Yeah.
And the reason we use that is because the multi-flash GOR, they're all at different conditions. And so we want to have an apple-to-apple thing to start with.
Yeah.
Because the most important is actually you get to the, you get to the composition. And when you get the composition, you can do all sorts of things, right? So this is a very good, people realize that the question asked about this. So if you use a similar approach like what we do, and then you need to do something to really mimic that difference, right? Because you don't want to put a 3,000 production GOR into that correlation and try to find out what is the properties, right? Because this is a plot, they're all based on a single base, single stage.
Yeah, that makes
the
sense.
same with our machine learning, that when we do the machine learning for 2,000 PVD samples in a conventional reservoir, and people ask us, what GOR do you use? We use a single flash. And our error is plus minus 30%. And we're a little bit lazy to correct it anymore, because there's 30%, you can just live with that.
Exactly. There's also a question about the paper, so that will be in that presentation. We'll have the paper references as well. But with that, we're going to round off and appreciate everybody joining the call today. And thanks again, Tao, for sharing this. It's actually one of my favorite papers. And then I realized it was actually a distinguished lecture. So I was like, okay, we need to get this up from the archives and show it to the rest of the world, because it's really interesting work. So with that, thank you again, Tao, for an excellent presentation, and thank you everyone for joining.
Thank you for having me.